in just a minute. What I'm basically going to cover is how do we use this new and burgeoning topic of machine learning in conjunction with space physics, right? How do we specify environments? How do we discover physics? And this is basically what I'm going to be talking about. I'll tell you some of the things that we've done using plasmaspheric density modeling. I'll show you some of the stuff we're doing right now using radiation belt specification models. And I'll show you some of the stuff that we're thinking about. In other words, things that are under development right now, things that are kind of prototyped, just to give you some flavor of where we're going with all these ideas and how we're using them. So using machine learning for science is different from just using it for specification, using it in industry. And there are a couple of important differences, and I'm going to highlight those as I go along. Before I start, I'd like to acknowledge a lot of the people that contributed to this talk in important ways. My student Donglai Ma, you'll see a lot of his work later on. Xiangning Chu, a former postdoc who has done a lot of the plasma density work and some of the high energy work in the radiation belts. And the research team, Qianli Ma, Chao Yu, who is now a professor at Peking University, Wen Li, Richard Denton, the late great Richard Thorne, Vasilis Angelopoulos, Seth, and of course the Van Allen probes team, whose data we use extensively. It's just a remarkable data set, a fantastic experiment that recently concluded. Okay, so before I get going, if you've ever been to any of my lectures, you know that they're highly interactive. And so I'm gonna have just a little tiny bit of interactivity to begin with. The question that I have for the audience right now, so please get your chat boxes ready. You just click those open. The question that I have for you is about the figure on the right-hand side here. And the question is, what is this figure? What do you know about it? What does it represent? Who drew it? What is it indicative of? And basically anything you can put down in this figure. And I'm going to give you 30 seconds. Drop your answers into the chat box right now. And go ahead. 30 seconds. Okay, Kepler's Isaac Newton figure, Kepler's orbital motion, escape speeds versus orbital speeds. Looks like the Earth. Okay, I'm not going to give it away just yet. Ballistic motion, fantastic, you guys. Okay, from Newton's Principia. Okay, so pretty much everyone has guessed it. So this is a figure. It's a very famous figure. It was first sketched by the great Isaac Newton in 1687. It comes from the Principia, of course, which describes the orbital motion of planets around, moons around planets, planets around stars, stars around, galactic centers. And the idea is very simple. He's using kind of a thought experiment to illustrate orbital motion. Here's how this figure goes. So this is, of course, the Earth. And what Isaac Newton is envisioning is a cannon on a very high mountain. That's on point V. The cannon is going to fire a cannonball in a horizontal direction with a certain velocity. So this is a very familiar situation. We put it up on a high mountain so that air friction, drag forces become negligible. And so when the cannon fires, the cannonball flies a certain distance and falls down to the ground. And that's depicted by the point D. Now we add charge to our cannon, put in more gunpowder. And so now the cannon fires with a greater horizontal initial velocity. So the cannonball flies to point E. Repeat this one more time and put in more charge this time. And so the cannonball will fly to point F. And the point is that when you add more and more initial horizontal velocity to your cannonball, at some point there's a critical velocity that when the cannonball flies in a horizontal direction, the Earth will curve away from it at exactly the same rate that the cannonball is falling down. And so the cannonball will achieve orbital velocity. Orbital velocity is about 7.5 kilometers per second. And indeed, we find that this is indeed true. And I'll show that in just a minute. If you increase the velocity further, you of course reach escape velocity and the cannonball continues to fly out of the Earth's gravitational potential well. So that's a thought experiment. And this was, of course, 1687, the first time that we know of that anyone has ever envisioned orbital motion. And this, of course, explains how all the planets and moons and even stars orbit around their gravitational potentials in the universe. So from 1687 to 1958, this was, of course, the launch of the very first orbiting spacecraft. This is the Explorer 1 on the left-hand side here. And this is an iconic picture. Here I've pictured William Pickering, a New Zealander who was the head of JPL at that time in the 1950s. James Van Allen, eponymously called the Van Allen radiation belts in his honor. Of course, he's the sort of mastermind behind this Explorer 1 satellite project. And Werner von Braun, a former Nazi military officer who was kind of a high-value acquisition after the Second World War, brought over to the United States to help develop the rocketeering program. He was kind of a rocketeering prodigy. He had incredible ideas, and you can just imagine what it was like having him work in a secure government facility in the 1950s, having come from Nazi Germany at the time. So it was a very interesting story full of exciting dynamics. But that was 1958. We had one spacecraft in orbit around the Earth. I think it lasted about 4 months, if memory serves. And of course, it led to the discovery of the Earth's radiation belts that I'm going to get to in just a few slides. Fast forward 60 years, and now we have the so-called heliophysics system observatory pictured here on the right-hand side. And you can see how the number of spacecraft has grown. We are now measuring every nook and cranny of the Earth's magnetosphere, of the solar wind, of right up to the solar corona, kind of right up to the base of the solar corona, with the Parker Solar Probe, the magnetospheres of other planets. In fact, right now there are something like 3,000 operational satellites in orbit. The number is something like 2,700. But what's happening right now is we're in the midst of a revolution. I think I'm preaching to the choir, so most of you are familiar with this. But this number of 3,000 orbiting satellites is growing dramatically. This is, of course, due to a little company called SpaceX, who single-handedly has concrete plans to launch 12,000 satellites. And in fact, there are sort of batches of 60 or so satellites, these Starlink satellites, that are going up virtually on a weekly cadence, right? Every 1 or 2 weeks. They have concrete plans for 12,000 satellites, but they have licenses in the FCC for something like 42,000. Conceivably, this will be something like 30,000 in the end, but projections and estimates place the number of satellites in orbit in the next decade, or less than a decade, at something like 57,000. It's kind of incredible. From less than 3,000 operational orbiting satellites right now to a factor of 20 in less than a decade. This is, of course, the low-cost access to space revolution. Over the past decade, the cost and complexity of getting to space has fallen dramatically, something like a factor of 10. The number of satellites that we are expecting to see in orbit is, of course, a tremendous boon. It's going to be really something that has never been experienced by mankind before, right? Kind of an eye in the sky on every patch of the Earth, virtually, on a minute cadence. But it also presents a tremendous space weather problem. So the importance of understanding, predicting, and specifying the near-Earth space environment becomes more important than ever. It's more than just a scientifically interesting problem. It is a societally important and very relevant problem. Just a few more words about the space weather implications here. Why is this important? What are the space weather issues? Well, in 1978, there was a famous paper written by Donald Kessler, which has subsequently come to be known as the Kessler effect or the Kessler syndrome. And the idea is as follows. If you have a certain number of satellites in a particular orbit, for example, low Earth orbit, say under 1,000 kilometer altitude, you have a certain probability of collision. Once you have a collision, right, once that, it's a non-zero probability. Once you have a collision, what you have is a resultant cloud of a few hundred pieces, a few hundred shards. And that increases the probability of the next collision dramatically, right? So if you have 3,000 satellites and you suddenly introduce, say, 300 extra shards into this orbit, you've increased your probability of collision dramatically. That means that the next collision is going to come a lot quicker than the previous collision did. And once that happens, you have another cloud of several hundred shards, and so it goes. And so there's this catastrophic effect where once you have a single collision, it's kind of a domino, catastrophic, exponential effect that may infect the low Earth orbit in a very quick way. And it could actually, in fact, bring down the entire fleet. So this is a very well-known problem, but to make things worse, the environment is not static, right? We know that when we have geomagnetically active conditions, we have very strong, very powerful closure currents that flow through the bottom side of the ionosphere. This, of course, heats the ionosphere. It heats the neutral atmosphere such that it expands, right? The scale height increases. And so the mass density at low Earth orbit, in other words, the drag force, which is directly proportional to the mass density, increases. And so if you're trying to do some kind of satellite tracking, orbital prediction, collision avoidance, there's this massive spanner in the works where suddenly you've increased the mass density, not necessarily uniformly. In some parts of the orbit, for some satellites at a particular period of time. And so you have a slowing down of some satellites, you have a slight drop in the altitude of those satellites, and suddenly your collision avoidance has been, as we say, thrown for a loop. So So these things are notoriously difficult to predict. We can maybe say in a statistical sense what will happen, but predicting event by event is very, very difficult. It's a very complicated problem, and yet an incredibly important problem for the coming decade. So now let me switch gears and talk about why I believe machine learning is an exciting, important, and promising approach for us as we think about the next decade of work. So I have 3 slides on this topic, and then I'll tell you what I actually mean by machine learning to begin with. So the first slide is data volumes. If we have a look at these couple of slides over here, I'm going to move my little control panel. So this is the terabytes of archived data at the Space Physics Data Facility. And you can see that over a decade period, the slide is a little bit dated, from 2005 to 2015, we have this exponential, or actually super exponential growth in the amount of archived data at the SPDF. Similar for the community's usage of SPDF services. This is monthly usage, and you can see this kind of big uptick here at the very end of the chart. And a very similar looking chart for comparative data volumes. In other words, what we're saying is the kinds of projects that we have these days are returning data in volumes that are exponentially growing, right? So here's, for example, the famous Solar Dynamics Observatory, and now returning on the order of a petabyte of data. The famous Square Kilometer Array, which is half located in my home country of South Africa, promises to return something like the entire internet's worth of data very, very soon after first light, sort of in the first 1 or 2 weeks. Just kind of a tremendous amount of data coming down the pipeline, which you can't even transport easily. You have to build data warehouses that are co-located with your measurements, because the data pipelines are just not big enough when you start talking about petabytes and exabytes. And so the way we're doing computing is actually going to have to be rethought in light of these big projects. A study done in Science a few years ago by Khan et al., this is on genomics data, but it's a very similar picture in the Earth and space sciences, showed that genomics data has increased by a factor of about 10,000 over the previous 6 years of that paper. Now, if you compare it to Moore's law, that's a doubling roughly every 18 months. That gives you a factor of 16 increase. That's the kind of increase that we're used to seeing, a Moore's law type of increase. But the amount of data that we have is far exceeding that of Moore's law. And so the question is, how do we extract the science from all this data? How do we make our understanding, our insight, follow anywhere close to the amount of data that we have, right? If we have 1,000 times more data or 1,000,000 times more data, is our insight 1,000,000 times better? Probably not. Why is that, and how do we address that? Okay, that's something I want you to kind of have in the back of your minds. The second question, the second case for machine learning is the limits of the current analysis methods. And here I'm showing two plots by a friend and a colleague whose name I'll withhold. I don't want to embarrass this person, but this is not a criticism, and I'm actually a co-author of a few of these papers. I just want to illustrate the limits of the current analysis methods. The way we currently do our analysis on satellite data is we do something like this. This is a paper from 2004. It shows you equatorial plasmaspheric His power plotted as a function of L shell, that's radius in these little dial plots, magnetic local time. And you can see it's subdivided by geomagnetic activity, so low, medium, and active conditions. And you can see that there are some major data gaps over here that we're missing. This is just satellite coverage under these conditions. But you can see that when geomagnetic activity picks up, we have a gradual increase in the wave power of plasmaspheric His. Fast forward about a solar cycle later to 2018, same author et al. Here the data volume has grown by about a factor of 100. So now here we have DE1, cluster, TC1, Themis and Van Allen probes by themselves just are a tremendous increase in the amount of data availability. And you can see that now all these gaps have filled in. There are still just a tiny little few dots, but the picture is essentially the same. As you increase geomagnetic activity, wave intensity grows, and you can see its distribution and characteristics here. And the question is, how would this distribution, how would this picture change if we increase the availability of data by another 100-fold, right? We might fill in a few of these little white patches over here, but essentially the picture will stay approximately the same. What I'm saying here is that the expressive capacity of these models, right? The ability of them to express all the nuances of all this tremendous data volume has basically been saturated. There's no more expressive capacity here. It doesn't matter if you put in 100, 1,000, or 1,000,000 times more data into this model. The model itself has reached its capacity and it's no longer expressive. And so this brings me to point number 3, a very quick point, just a few random thoughts about, well, what should we be doing? Firstly, a couple of notes. We have a ton of archived data in SPDF and other archives. And we've collectively spent billions of dollars, and by we, I mean not me, but governments around the world, billions of dollars. And a lot of these data sets are not really being accessed very much. And so why? Couldn't we just bring them back to life in some way? Secondly, as I said, we have large and increasing volumes of data, and we need a method that would exploit this huge volume of data. Related to that, we need a model that, as you increase the amount of data, it grows with the data. So for example, the static plots I showed in the previous slide have kind of stopped growing. They filled up their expressive capacity, and they're not growing, kind of like not stretching anymore to accommodate all this data. And what I'm envisioning here is it's kind of like Google Maps, right? When you download a map onto your phone, it's kind of blocky and pixelated. But as you wait longer, the picture itself sharpens up and you start to see a lot of resolution. And this is what I want to see in my models. As you add more data, the model becomes higher resolution and more expressive, and it expresses more of the details and the nuances of what's going on. And finally, I've alluded to this a little bit, but nowadays we are starting to move away from single satellite missions. We're starting to think in 2s and 3s and 5s, sometimes in 30s, right? If you're Elon Musk, you might think in 10,000s of satellites. We have all these amazing distributed arrays of measurements, and we don't want to treat them as individual points that are not related to each other. We want to somehow stitch them all together so that our analysis method knows that all these points are spatiotemporally related to each other. So this is my point number 3 for machine learning. And so I hope that I've laid down some groundwork, at least of what we are thinking about, what we are requiring of the new age of analysis methods over the next decade, right? To kind of accommodate these big projects, these big ideas that are happening in the community right now. So let me tell you about what machine learning is. This is a famous picture of Arthur Samuel, who is considered by most to be the father of machine learning. And here I'm showing him in front of the IBM 701. And he is essentially the person that conceived of this idea of machine learning. Now, the idea was that he wanted to create a program that would play checkers, but at a level better than himself. Now, how do you do that? In the traditional way of programming, you need to provide a list of instructions. I'm, again, preaching to the choir, you all know this, but we provide a list of instructions to a certain program that tells the program what to do under every single condition that may arise, right? The program knows exactly what to do and it follows sequentially that sequence of steps. Now, that's all good and fine, but if you program your checkers playing machine in this way, then you, the programmer, always know what it's going to do at every particular time, and you can easily beat it, right? You can anticipate what it's going to do. So he came up with this alternative idea, and he said, how about instead of specifying what the machine is going to do at every junction, I'm going to just give it some rules. I'm going to have it play the game of checkers over and over again, and I'm going to tell it what are good moves and what are bad moves, and I'm going to have it retain the good moves that lead to a higher probability of it winning, and I'm going to have it discard the bad moves that don't go anywhere, and I'm going to have this code play against itself thousands and thousands of times, and I'm going to have it optimize for winning the game. And so he did that, and lo and behold, he created the very first machine learning code. Right? In machine learning, the program automatically creates rules for itself from the data, and here it is learning from its own experience. In fact, when this checkers playing machine was shown at IBM for the first time, the stock price jumped over 10% overnight. People suddenly twigged onto the idea that computers are more than just fancy toys that could do some calculations for you. They could do something that was beyond human capability for the first time. In fact, his checkers playing machine went on to beat the Connecticut state champion in 1963, I believe. So this machine reached a high level of sophistication. And remember that computing was very limited at the time too. So an incredible feat. The definition that he wrote in this famous IBM journal paper in 1959 was that machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. You don't program the rules of what the checkers playing machine needs to do. It figures out those rules by itself from playing, from its experience, trying to optimize for winning. So that's the basic idea behind machine learning. How do we apply machine learning to heliophysics? Well, this is a problem that I started thinking about a few years ago. And the question, the goal is the following. Assume that you have a satellite orbiting around the Earth like so. And so at any point in time, at any point in space, R, it is collecting a measurement, right? Let's call it some measurement Q. You can think about number density, right? Electron number density. And so it collects this measurement at one point in space, and then collects another measurement a minute later, and another point in space, and another minute later, another point in space. And so what you end up with after the whole mission is you end up with several years of data of a time series, but only at one point in space at a time. And that's great, but it's not terribly useful. What you really want is you kind of want to turn this program, this data set on its head, and you want lots of points in space at a single time point. You want to see a 2D or a 3D representation of your data, right? Kind of in a 2D or 3D environment, reconstructed from this very long time series. And so this is what my initial thought was. And so to solve this problem, I trained an artificial neural network to predict what the satellite should see at any location R at any time t, based on a time history of a geomagnetic index. And for this purpose, I used the SIMH index, and I looked at electron number density from the Themis satellites. I'll talk about that in the next slide. But lo and behold, the program was able to capture the dynamics of the system, right? It was able to reproduce, it was able to take this very long time series of Q measured at only a single point at a time and turn it into a set of rules and a set of dynamics internally coded into the machine learning parameters that would then reproduce my quantity. Just a few extra notes here. Q can be any quantity, and I'll show you a couple of different examples of what Q can be. I used an artificial neural network because it's a universal approximator. It has this property like a polynomial expansion or a Fourier series that the more terms you add, the more accurate your approximation can become, right? So that's a universal approximator property. And I use the deep neural network because the deeper your neural network is, the more complex the basis functions are that represent the system. It's kind of like a Fourier series, but the deeper your network is, the more complex are your sines and cosines that are the basis functions. So you can, in a more compact way, represent more complex relationships between inputs and outputs. We train on neural network, and the whole idea here is that it needs to be able to replicate the dynamics of data that it has not seen before. It needs to be very generalizable, right? The object is to pick the most generalized representation of our data without overfitting. So that's the basic idea. And out of this came out a 2016 paper called A Unified Approach to Intermagnetospheric State Prediction, where I did exactly what I just described. I took data from the Themis AD and E satellites. It was about a 7-year time series, sampled at a 5-minute cadence, and using the location of the satellites and a 5-hour look back window of the SIMH index, also at a 5-minute cadence, I was able to train a neural network to reproduce the electron number density throughout the whole of the spatial domain. And here you can see this is a storm occurring on 9th of March 2008. The red dashed lines represent time slices, and at every one of these time slices, I probed my neural network to say, what is the density at all locations? And so right away, you can see that the neural net has learned that there is a dense inner core of your plasma right here, the plasmasphere, of course. There's kind of a sharp edge called the plasma pores, and there's a plasma trough here, right? A sort of a low density region outside the plasmasphere. But I hate to sound like a salesman, that's not all. As your geomagnetic storm evolves, the neural net has learned that the plasmasphere erodes starting from the night side. It extends in the day side, right? There's no plasma physics model. There's no, model that I've given to this neural network. It has figured out these dynamics on its own, that the plasma should evacuate or convect out of the day side when you turn on the convection electric field across the night side. Your plasmasphere erodes, and when you turn off your convection electric field, a little, where am I looking? A little plume forms right over here, which starts to co-rotate. All of this, the neural network has learned and encoded by itself, just by looking at the data and then being asked to reproduce it. Okay, so just an incredibly powerful approach. Here is an animation showing a very similar thing. This is now a refinement of the previous paper written by my then postdoc Xiangming Chu in 2017 on the erosion and refilling of the plasmasphere. This is a little bit jumpy because we're going at quite a fast clip here, but you can see the same thing. Plasmasphere erodes, evacuates out of the day side, the plume forms, co-rotates. The physics of the entire system is baked into this model, right? All the physics is baked into the data, and it's now baked into this model. Here's just an example of a time series, and here I'm comparing the Themis A, D, and E satellite observations over a few-day period in February 2011. Observations are in black. Model predictions are in red for an out of sample period. And you can see that the model pretty much overlays what we observe from the data, right? You have a very, very good agreement there. The same thing can be done in 3 dimensions too. So here we've used a number of other satellites. So we had to switch away from Themis because Themis is predominantly equatorial. We now switched to 4 other satellites, which are described in this 2017 paper. But now we have a whole 3-dimensional dynamic system that we stitched together from 4 disparate satellites. Let's see, speaking out of memory, Polar, IC, DE1, and what am I missing? There's one other that I'm forgetting. And you can probe this 3-dimensional system in any plane that you wish, under any geomagnetic conditions, preferably that it's seen. And so, okay, so we've done this. The model bakes in the physics of the system. And you might want to say, well, so what? So how do we use this? And so here's just a 1-slide example of how do we use these models for science. Okay, so the point that I want to make here is that oftentimes in industry, when you create a machine learning model, it's the answer, right? You want to predict Amazon orders for a particular book at a particular time, and you train a machine learning model so that you can anticipate a surge in demand at a particular time and get all those books ready on your shelves and all the shipments and everything ready. And so that's the answer. Okay, in industry, the predictive model is the answer. In science, we're a little bit more picky than that. The machine learning model is not quite the answer. It's a tool. It is a representation of our data, right? What I showed you previously is basically just our own data, but it's represented to us in a way that we can more easily understand and interpret. And let me show you what I mean. This is an example using the 3-dimensional, the DEN 3D model that Xiangning developed. Again, it's showing a storm period. Let's look at the second slide here, part B. SimH is the same as DST for those who are not familiar with this. You can see a little dip in SimH showing the buildup of the ring current. And so we have a minor storm going on here. And this is 0.1 times the absolute value of AL. So it's a proxy for injections from the tail, right? Fast flows, if you will. So you can see that there's a couple of injections going on here in the midst of this storm that's going on. Panel C shows you the plasma density on the on the noon midnight plane. I think this is actually the day side. And in color is shown the log of the density itself, and you can see the plasma pores. And when the storm hits, the plasma sphere erodes as it should. We understand that data. That behavior well. But look at what happens with the low L shells. We see these enhancements. And at first, I did think that this was a glitch, an error of the model. It was doing something that it should not be doing. And then as we dived into this further and further, here are line plots at various L shells. You can see that there's a slight little bump here at the lower L shells. And if you normalize it by the previous values, you can see that the relative percentage increase is something like 200%. We have these very dramatic enhancements at low L shells, like L of 2 to 2.5 over here, in association with injections from the tail. You can then do a 3D slice, a meridional slice, and you can see that these density enhancements are coming out of the ionosphere here. And in fact, we then went back to our original data. We saw that these enhancements were in there, and we went to image RPI data and other image in situ data. And we've shown cases where indeed on the night side, in association with injections, we have these temporary spikes in the electron density at low L shell, these low L shell spikes. So this is a discovery. It's a machine learning enabled discovery because we use our machine learning as a tool. We were able to see our data in a way that you just can't see these kinds of enhancements from a time series. Right? It's very difficult to discern that this is the thing that's actually happening. So inside discovery, right? Discovering new physics using a machine learning model. Okay, let me change gears now and talk about radiation belt dynamics. And in particular, I'm going to talk about whole environment modeling. We not only model individual events or individual energy channels or particles. We now are interested in modeling entire environments. So for those who are not familiar with radiation belts, this is a very, very quick one-slide primer. The radiation belts is basically are composed of a population of energetic electrons, and by energetic I mean affected only by magnetic gradient drifts of roughly MeV energies, and they're magnetically trapped. In other words, they gyrate about magnetic field lines, they bounce between magnetic mirror points, and they drift around the Earth on timescales of minutes or tens of minutes. They are a space weather hazard for spacecraft. They can do all kinds of things to spacecraft, like charge up the outside parts, degrade solar panels, borrow into electronics, cause spurious commands, charge up dielectrics on the inside. So they can do a whole bunch of things to our satellites. And additionally, from my point of view, they're scientifically interesting. There's a whole bunch of neat plasma physics that goes on. There are a whole bunch of waves that do all kinds of wave-particle interaction things to these energetic electrons. Sometimes the same wave can do different things to particles just when you crank up its intensity. Those are called nonlinear effects. So there are so many different things, and nature acts as this natural particle accelerator, accelerating particles from 100 keV up to several MeV. It's been doing it since time immemorial, and every planet with a magnetic field that we know of does very similar types of things. So a very fascinating universal process that's also a space weather hazard. This is a plot from one of Dan Baker's famous papers showing Van Allen probes A and B data for 1.8 MeV electrons. And you can see that as a function of L shell and time, there's a lot of variability, even in these very, very high energies. There are injections, there are decays, times of very low fluxes, times of very high fluxes, and so on. So a very interesting structure indeed. The way we model radiation belt dynamics is with the so-called FuckerPlunk equation, a very well-known equation. And I'm not going to delve into the details of it, but what it says is that the phase space density at any point in L shell and time is dependent upon these gradients of the phase space density in pitch angle, in momentum, that's P, and there's another term that usually accompanies this equation in L or L star, kind of a spatial gradient. Importantly, when we talk about physics-based modeling of the radiation belts, this is what we mean. But let's just unpack this a little bit. What does the physics-based actually mean here? Well, it means that all the physical processes that I talked about, the various waves and wave-particle effects, their distributions, their intensities, are all packed into these d alpha alphas, d alpha p's, dpp's. These diffusion coefficients are basically parameterized expressions of wave properties, intensities, frequencies, spatial distributions, spectral distributions, temporal variations, and of course, different plasma wave modes. So all the physics is crammed into here, and they're parameterized. We feed in typically solar wind parameters, solar wind quantities, and geomagnetic indices, and we scale all these parameters according to those values and represent the effects of waves on the particles. We also need time-varying boundary conditions, right? This is a 6-dimensional cube, pitch angle energy in L shell. And so the boundary conditions vary as a function of time, right? That needs to be specified from the data somehow. I think somebody is unmuted there. Okay. And of course, initial conditions and the driving conditions, right? All of this needs to be specified externally. In fact, if you draw a big red box around this equation, what you have is a transformation. You have a whole bunch of inputs, such as geomagnetic indices and their time histories, solar wind parameters and their time histories. You take all those quantities and you transform them into a radiation belt variation. It's just a transformation, right? That's what we do. This is a paper by Sasha Drozdov, one of the most recent examples. And this is what we do. We parameterized EMIC waves, His and chorus, and we see how adding and taking away these various effects or parameterizations affects the radiation belts. And when we have something that looks a little bit like the observations, we say, bingo, we understand everything. That's kind of like how we do radiation belt science. But what if we start from this parameterization and we say, how about we just take all these inputs and we learn the transformation, see the radiation belt variation? So that's exactly what we've done. And in a very similar way to the electron number density, let me just watch the time here, which is running away. We can now take 1.8 MeV electron fluxes, like I showed from Dan Baker's paper, and we can learn, we can train a machine learning model to learn the variation along the satellite trajectory. And then we can withhold some data and we can test how good we're doing on these holdout data sets. Here's an example of a storm, and I'll focus on this January 5th to 7th storm in 2015. And you can see this is the observation from RBA. Here's our model predictions. And this is out of sample. And our model learns what the radiation belts are doing very, very accurately. Here's a reconstruction of what the data looks like everywhere. And this, I actually fear to say, is already an outdated model. We have a newer version of this model, which we've tuned a lot. Here are some error metrics, and we've done a ton of this. This is going to be in a paper coming out by Xiangning Chu. On the training data set, what we use to actually train a model, the prediction ability is something like 99%. But when you take it to data that the model hasn't seen before, we're still at about the 95% level. We believe that with these very high capacity, very expressive models, we're doing as good of a transformation as it can possibly get. Physics-based, not physics-based, this is as good as it can get. All the physics of the system are now baked into this model. Okay, this is 1.8 MeV. We can do exactly the same for 2.1, 2.6, 3.4, 4.2 MeV. Here are the line plots, and here are the reconstructed models. This is a little bit too smooth. I'm sorry about that. Again, we have error metrics for all of these quantities. We can then move down in energy. These energies are actually a lot more complicated. This is the MAGICE energy range, and we can apply exactly the same methodology to the 0.1 to 1 MeV electrons. This energy range is complicated because it now has an azimuthal dependence. And here I'm showing a model developed by my student Donglai Ma, and you can see that the model now captures this azimuthal behavior. The drift periods of these tens of keV particles are on the same order as the decay timescale, which makes them complicated. In fact, this energy range includes drift physics, convection physics, losses, magnetic drifts. It is a very complicated system, and it's a very, very key system. In terms of radiation belts, it provides your seed electrons that get accelerated, your source electrons that excite plasma waves, and these kind of ring current energies or plasma sheet energies are the source of many, many different kinds of plasma waves. So they're very complicated to deal with, but our machine learning algorithms are able to capture and represent our data in this way. And in fact, the way we typically deal with such particles is either with a statistical plot or with physics-based models. There's nothing in between. And so this is the in-between part. It is your satellite data represented in a dynamic form. Okay. I promised the whole environment, and so now we can move from in situ trapped fluxes to precipitating fluxes. This is a model of pose data, precipitating data for 30 keV electrons. This is developed by my researcher who works with me, Seth Claudepierre. And it's a complicated and busy plot. We see a bunch of error metrics on the right-hand side here. But what is being shown is a number of pose data from a number of pose vehicles for 30 keV and above, and a machine learning algorithm that has learned to replicate the observed data, right? The red is the model, the black is the observation. These models are not as good as the trapped models. There are a whole bunch of issues that are involved, firstly in low Earth orbit, secondly in the pose vehicles themselves that we need to be mindful of. But we're doing at the 90% level So still extremely good, about as good as we can get, we believe. Okay, precipitating fluxes. What do you do with precipitating fluxes? You can feed precipitating fluxes into a physics-based model, and here you can see this is based on the Rees 1963 model of pair production. It's been a little bit jimmied and fixed with a collisional friction force at the lower energy range. And so now we can reproduce electron perturbations, electron density perturbations as a function of altitude based on our precipitation model. And so we're now going to marry a physics-based model of ionospheric conductivity modifications together with a machine-learned precipitation model. And so this is what we get. So now we have a specification of precipitation as a function of L shell and MLT or latitude. Take any one of these pixels and feed it into a this conductivity modification code, like I showed in the previous plot. And so you can get this three-dimensional modification of electron densities at any point in space and time. Okay, this is tremendously useful for people who are worried about things like scintillation, right? Gradients in your total electron content in the ionosphere, kind of disturbing the signals in that way. So we have this way of marrying machine learning and physics-based models. That's just an example of such an application. Finally, I've talked about the application of machine learning in physics discoveries when I talked about plasma densities. Here I'm going to talk about more like applications. And so we are partnering with Space Environment Technologies, SET, our small business partner. This is part of a space weather operations to research project where we're now taking our models that we've developed and we're making it available to the whole space weather community. And so this is done through SET. Our models, this is an early generation model that has gotten incorporated into their space weather services. And so this is called the Orbis model. Outer Radiation Belt Information Systems, Orbis is what it stands for. And we're now updating to our newest generation models. So this is available to space weather customers already. And we believe that this is the way we should be doing it. Academia should be working with industry, small business in particular, to be taking the fruits of our labor and making them available to the community in this way. Finally, and so this is the final part of my talk. I'm running a little bit late here, but let's talk about what's next. How are we going to use machine learning in the next decade to do physics, right, in conjunction with physics? So this is a very busy slide. It comes from a paper by Rudy et al. In 2017. And what it shows here is a simulation. This is a Navier-Stokes numerical simulation. And what is the idea? The idea is, how about you take data and you train a machine learning algorithm to learn the partial differential equations that would have resulted in that data that is observed? What are the driving partial differential equations that are underlying this data? And there are actually algorithms that will automatically ferret out these fundamental equations. So no more kind of this forward modeling and switching processes in and out to see what works. Why don't you just take the data and tell it what is the equation that controls you, right? And here you see examples of KDV and Burgers and Navier-Stokes. And you can see how well, so this is the identified dynamics, and you see that it comes very, very close to the true Navier-Stokes that produce the system, even sampled at very sparse points. Okay, so this is from Rudy, and I'll show you how we apply this to radiation belt dynamics in my remaining couple of minutes. Here's a simulation of phase space density. This is just the radiation belts relaxing as a function of L shell and time. These were the equations that were used to model the system. And these were the leading terms. U sub x and U sub xx are df by dl and df by dl squared. These terms, this term and this term. This is what drove the system. What we've done is we've taken the simulation and we kind of messed it up a little bit. We put a satellite orbit through here. We messed it up with a whole bunch of noise. And we said, how would this look in a real life situation? And the first answer is, when you add noise, the system breaks down. And so the wheels come off but with some clever manipulation and using a bunch of other tricks and techniques. I'll just throw out group sparsity for those who are familiar with this, and volume averaging. We're able to discover in the most intense part of the radiation belts, we're able to discover the lead driving terms of the system. And so we're getting closer and closer to reality, okay? PDE discovery. We want the data to tell us what the equation is creating it. The second part is how do you mix together physics with your machine learning models? In our previous models that I've shown, it was all data driven. It was just, here's the data, and create a model that will reproduce that data for me. But we as humans, we can take a fairly limited amount of data, and we can very accurately extrapolate that data because we kind of understand intuitively how the system functions. We have an understanding of the underlying physical laws. How about we imbue our machine learning models with such an understanding? So here's an experiment that we did with online, and we have two magnetic dipoles. This magnetic dipole is representative of the Earth, and it has its own magnetic field system. And this larger magnetic dipole is representative of, for example, magnetic flux rope. Okay, and so you have interplanetary magnetic field flying in from the left-hand side, and this comes from an animation. So we messed around the left side of this, kind of like a CME flying through or a flux rope flying through, and we sampled our space very coarsely to see how our machine learning would reproduce the data. The trick is, instead of just having a mean squared error between the data and our model, we introduced the second term. Enforce divergence of B is equal to 0. Make it divergence free with some parameter alpha. So the alpha is like our insistence. Conserve this law scaled by this quantity. When alpha is 0, it's just a machine learned model, and you can see here are two instances in the simulation. This is the ground truth, and here you can see that the model does pretty well for the most part, right? We actually reproduce the majority of the simulation, except for these bumps and squiggles and wiggles over here, and that's not right. That's clearly not in the driving data. Increase alpha to 1,000, and suddenly these squiggles straighten out, and increase alpha even more, and you can see that now we have something very similar looking to what we had in our original data. Again, very, very sparsely sampled, and a time varying animation where this all comes from. This is just one snippet of it. So we are kind of penalizing ourselves and making it very difficult for ourselves so that we can see how well this approach is really working. And it really is working pretty well. It allows you to train much more accurate models with noisy and sparse data. So the machine learning models of tomorrow are going to have physics-based laws baked into them, right? The laws that you really, really believe, like divergence of B is equal to 0, can be enforced and can create a model that's much more realistic for a smaller number of data points. Finally, I'll just throw this out because my time is just about up. But a very new branch of work is using AI or machine learning, I'm using them interchangeably, to solve PDEs in a dramatically more accurate way, and dramatically faster and more accurate way than traditional Crank-Nicholson solvers, for instance, up to 1,000 times faster. And here you see the ground truth and the prediction. And this created a huge buzz when it came out last year, October 30th, 2020. So you can imagine that perhaps, maybe, the large-scale MHD simulations of tomorrow will be based on techniques like this and may not even require supercomputers to run anymore. Maybe they'll be run on much smaller resources because of these incredible techniques that are coming up. As a fun tidbit, this made so much media that even MC Hammer tweeted about it. You remember MC Hammer? You can't touch this. Okay. And on that note, let me conclude and summarize and say that scientific data is growing, and we're thinking and we're experimenting and we're playing with machine learning techniques to deal with large data sets, to reconstruct them, eke out basic physical processes. And then in the next steps, we are thinking specifically about what are the upcoming technologies and how do we include them in space physics, PDE discovery, physics-informed neural networks, or machine learning in general, and ultra-fast PDE solvers, which we have not played with yet, but I'm throwing it out as an idea for the community if you're looking for interesting avenues that may be promising, hopefully. This is something to look at. So let me conclude right there. Thank you very much, everybody, and thank you again for this invitation.
Well, Jacob, thank you very much for giving quite a fascinating talk. I mean, especially with MC Hammer at the end, can't touch this. You know that this is exciting stuff when we venture into comments like that. So, but it was very interesting, and that was also reflected by the questions here in the chat, which I'd like to get to as well. Just because it is the top of the hour, I want to mention for those tuning in next week, we are going to continue in this space weather theme. Christopher Balch is going to be discussing NOAA's Regional Geoelectric Field Modeling Project and how to mitigate space weather impacts on our power grid. So be sure to tune in next week for that. And so, yeah, if you do have time, Jacob, I'll just jump into the questions here from earlier. And okay, so the first one that came in, there were a couple from Hamid, I believe, and he says, back to the earlier slides about just possible collisions with these satellites and just how many satellites we have in our near-Earth system. He asks, how dense would satellites have to get to start worrying about them actually colliding? If there's a
I don't actually have numbers here. I'm sure that some of our space weather colleagues, I saw Howard Singer on the line. I don't know if Howard has any real numbers. I don't know what the critical number is for that. But, I would imagine that if you put 60,000 satellites into a relatively small orbit like Leo, that could be an issue. Something I didn't mention before, but not to give anybody any ideas, but if you are a bad actor and you want to create havoc, one thing you could do is aim your high-powered laser beam into space and destroy a satellite and create shards. And this is something that the US government is well aware of and is thinking about. What are different ways to cope with that kind of very asymmetrical attack? This is a real threat. It's something that the space physics community should be aware of. The space weather community is aware of and thinking about. So there are some real kind of serious consequences to the space weather thing.
Mm-hmm, certainly, yeah. And also in those earlier slides, a second question from the same person there. So is there reason to believe that there actually is some additional use to all the extra data, even if it's already saturating our existing models, like you had mentioned previously in some of those early plots? Sure.
Looking at different scales, looking at the interconnectedness of scales, nature is fascinating. Bob Clower always used to tell me that whenever you look at data, you learn something new. So why isn't the same true with models, right? I mean, if our models get down to greater and greater granularity, there's kind of a tremendous wealth in the small scales that then feeds into the larger scales. And I think this has been traditionally very hard to model, to do both at once. I myself kind of do both ends, global modeling and the microphysics of the way particle interactions. Bridging those two worlds is very difficult, but I think this is where we're heading with humongous projects like the Square Kilometer Array, for instance.
Certainly. Mm-hmm. Okay, great, thank you. And so moving on to the next question here. So Daniel De Silva was asking, just pointing out that one of the common warnings about neural networks is that they're strong interpolators and weak extrapolators, where the difference between what is actually an interpolation and extrapolation may not be obvious. So he's wondering, how do you integrate this into your confidence of learning from it? Basically, how does it influence our confidence in these models, I guess?
Yeah, so the difficulty of extrapolation of neural networks has been discovered by Wall Street traders in the 1990s pretty successfully. So yeah, don't use them for extrapolation. Neural networks are very good at interpolating very densely sampled spaces. In other words, you want a space that's very, very densely sampled so you can pick up and tease out very subtle, repeatable effects. That's what it's going to do for you. There's a whole branch of study on quantifying uncertainty why am I thinking QE? Quantifying uncertainty quantification, which tells you when you have a certain prediction, it's just 1 point, but around it there's a confidence interval, and it may be complicated. It may vary as a function of space and time, and so that needs to be understood, as well as its extremes. How bad could it possibly get? And so, so that's a very important consideration. Yeah. So no, we've experimented with Gaussian processes with our friend and colleague Enrico Campariale to kind of bolt on a Gaussian process on top of our neural network prediction, and that seems to work pretty well. But there's much room for improvement.
Certainly. Okay, great. And yeah, the next couple of questions here getting into some of the, I think, machinery of how this works. So Boris was asking, data comes in various flavors, and what do you do to prepare the data, say, from various satellites toward creating these machine learning models? And maybe what software or programming language do you use to run them, and the models, the codes, the display, etc.?
Yeah, I hate to reveal my grandpa status, but I am a MATLAB user, whereas everyone in my group is a Python user, and so we use Python generally. TensorFlow is a fantastic tool. Not that I'm endorsing or recommending it, but just something that is very useful. Okay, something in terms of data preparation, something that my machine learning class always finds very heartbreaking is that when you actually get to do machine learning in the wild, 95% or more of your time is just spent with cleaning up the data, making sure it's intercalibrated, making sure that it's consistent, no funny jumps or squiggles, or you get the idea. In Wall Street, you have kind of tiers of machine learners. The people who train the models are kind of like, there's relatively few of them, and they're all at the sort of PhD level, and they look a lot like people like physics and math graduates. And below them, there's a whole tier of kind of like young interns, and there are generally rooms of such people who get the data in, and they have a whole bunch of ways of cleaning and calibrating and cross calibrating, and so it's kind of so there's like a whole extra effort that is just focused on making sure that your data is good and clean before it gets to the the sort of predictive model stage. So we as scientists, of course, do it all ourselves. You got to spend a lot of time, as they say, garbage in, garbage out. Sometimes non-garbage in and a little bit of garbage out. So you gotta really, really be careful. All right, start off with simple cases that you understand. Train your models to make sure that it's working right, and go through that spiral many times. There's no substitute for domain expertise.
Certainly. Great. Okay, and a related question, it may have, you sort of touched on this already, but Ankush was wondering what type of neural network architectures are used for these predictions that you showed in the presentation?
Yeah, the answer to that is we don't just have one model, we have thousands. At the very least, we have thousands of models that we train, and we tweak everything from the depth of the network to the width, to the architecture, to the connectivity of the network. We experiment a lot. So there isn't just one, but the very rough guide is a network is typically, it's good enough when we have 2 or 3 hidden layers. The width of it, especially in the first layer, comparable to your feature set, right? So if you have an input vector of 100 elements or 1,000 elements, typically your first layer would be roughly of that order within a factor of 2. That's kind of like a very rough rule of thumb.
Great. Okay, thank you. And yeah, I think these next couple of questions are in the same vein, maybe stepping more to the practical side of things. So Allison was wondering, how important is it that we actually have in situ observations everywhere all the time if machine learning algorithms can reconstruct certain parameters accurately enough?
Yeah, that's a really good question. Thank you, Allison. Okay, if we had infinite understanding of our system, you might think 1 point of observation everywhere in the entire space should be sufficient. clearly we don't have an infinite understanding of our system. And so we need observations to the degree that we're missing certain things. So the models that I've shown can reproduce about 95% of the data that it's seen in the Van Allen probe's error. What about things that it hasn't seen, right? There's always that question. There's also always the question of kind of what is it missing? And can you specify better driving parameters? So you can always do better. So I think until we have a perfect understanding of our system, which I don't think we ever will, observations are going to be a key and integral part of any kind of a prediction scheme, a realistic kind of bread and butter scheme that you can actually rely on for space weather predictions. Incidentally, the models that we train are all nowcast, so they use parameters of geomagnetic indices and solar wind from now going backwards, even up to 30 days for the very high energy models. But we can run them into predictive mode as well. So we can train our models just based on DST or SimH alone. And there are some algorithms, for example, Ken Tabuska has the anomalous algorithm, which can predict out DST several days ahead. We can run our models in predictive mode. The model is as good as the prediction of your driving conditions. And as you might imagine, this is the weak point, right? This is the point that is very, very, very tricky to get right. And anomalous works pretty well under some pretty specific conditions. And so I think one of the keys of space weather prediction is going to be kind of getting that piece right. Can you predict anything informative for me? Anything at all? Anything about the solar wind, anything about geomagnetic indices? The further out we can predict these quantities, the better we can make the models that are kind of bolted on top of those predictions. And so for those who are just starting out and thinking about important problems, I think this problem is about as important as it gets for the space weather community.
Certainly. Yeah, great response. And in the interest of time too, I think we still have some questions trickling in, but maybe just the last couple, if that's still okay with you, Jacob. Let's touch on this here. So it looks like Connor was asking, basically again, sort of in that practical vein of how we might actually implement these methods. He says, machine learning experts can spend their entire career studying and developing these very complex machine learning architectures and improving their performance. But as space scientists, how do we how do we balance that desire to improve these models with the fact that it can be very time consuming to really dig into all the details of this optimization?
Yeah, that's a really good question. So I think as space physicists who are interested in machine learning, it's a bigger burden. You kind of have to be an expert in both domains. Now, you don't have to go into the complete nitty-gritty of machine learning, but you can't just take a pre-canned algorithm out of the box and apply it, because very quickly the wheels fall off and you need to know what's going on. So you need to know machine learning in enough depth to understand, kind of like Fourier series, right? We use them to create spectrograms. I mean, you don't have to be an exact expert and understand all the complex mathematics that go into it, but you got to know the basics. And so it's the same thing with machine learning and in fact any tool. People fall on different parts of the spectrum. Some people come from the machine learning world and educate themselves on space science to the degree that they understand the problem and what's important, and kind of like what's missing right now. Space physicists like myself delve into the world of machine learning and understand to a sufficient level how the machine learning algorithms work so that you can understand what they do and what their limitations are. So in conclusion, you have to know your tool well enough to apply it confidently.
Great. Yeah, excellent answer there. Yeah, and I think just skimming through the questions, I think you really captured the heart of what folks are asking, and maybe in the interest of time, we'll probably leave it there on that conclusionary note. But I definitely want to take this chance to thank you again, Jacob, for just a fascinating presentation, and that was evidenced by just the questions and the interaction, of course, throughout the chat as we went along. So yeah, thanks again very much for your time and for sharing with us these exciting discoveries and some next steps for our field as we go forward.
Thank you so much, everyone.
All right, thanks again. Have a good week.
Bye.